In this video, we're going to prove this same explicit formula for the number of derangements, this time using the principle of inclusion and exclusion. And the way that we're going to do that is by finding the number of permutations which aren't derangements. So how would I find a permutation that isn't a derangement? I'm not going to do the full proof here. I'm going to sketch it in and let you fill in the details. But let's go ahead and start. How would I find a permutation which isn't a derangement? What permutations aren't derangements? Those that fix or send to itself at least one element. So let's try to count those. How many permutations fix at least one element? Well, what I could do is I could choose an element to be fixed, one of my n elements to be fixed. And then after I fix that element, I can just find whatever bijection I want of the remaining ones. So that will be n minus 1 factorial. Find a bijection of the remaining ones, of the remaining elements. So just because we're going to get inclusion exclusion involved here, I'm going to draw some Venn diagrams that might let us think about some stuff. So let's let this be things that fix 1. Let's let this be things that fix 2. And this be things that fix 3. We're just going to consider derangements of 1, 2, and 3. So looking at derangements of 1, 2, and 3. And I'm not going to write out explicitly what derangements fall in which thing, but I just want us to be thinking about the Venn diagram. So essentially we decided, hey, I'm going to pick one of these bubbles. Am I going to fix 1, 2, or 3? Sorry, I should not have written the word derangements on any of these, because these are all specifically not derangements. So this is bijections. So we have things that fix 1, things that fix 2, things that fix 3. And then outside of this would be, derangements. They're living outside. They're not in any of those bubbles. So the reason I say this is basically we could choose one element to be fixed, but there might be some overlap. And choosing an element to be fixed basically lets us look at one of these whole circles. So in order to start subtracting the overlap of those circles, I need to use inclusion exclusion. So how many ways might I have some overlap? Well, I might have some overlap if I choose 2 elements to be fixed, and then I permute the remaining of those. And then I might have some triple overlap if I choose 3 elements to be fixed and then permute the remaining. And then I might have some more overlap if I choose 4 to be fixed and permute the remaining. All the way up to, we see that the negative sign is in front of, well, actually, I don't like that. We'll say n plus 1. You know what? I'm not going to do that. I'm going to write this a little silly. I'm going to write this as minus -1 to the n of, I'm going to choose to fix all of the elements and then permute the 0 that remain. So choose 1 element to be fixed, permute the rest, choose 2 to be fixed, permute the rest, choose 3 to be fixed, permute the rest, choose 4 to be fixed, permute the rest. And since this is using the principle of inclusion exclusion, we'll have this alternating sign for each. So remember, these are the things which aren't derangements. So these aren't derangements. So how many derangements are there? Well, there's n factorial bijections. And now I want to subtract the derangements, which is going to basically flip the signs in front of each of these. So n choose 1 times n minus 1 factorial plus n choose 2 times n minus 2 factorial minus n choose 3 times n minus 3 factorial plus all the way up to, and now I can go ahead and put a positive sign, make it negative 1 to the n, and choose n of 0. In fact, I'm not even going to write that as 0. I'm going to write that as n minus n factorial, which we can go ahead and write in a little summation. This is going to be the sum from k equals 0 to n. And before I write my summation, let's just for good measure make this n choose 0. This is going to be n choose k. I'll put the sign up front. This is going to be negative 1 to the k times n choose k times n minus k factorial. And that is almost what we want. I will leave it up to you to do the final algebra you need to show that this is in fact equal to negative 1 to the k times n factorial over k factorial. But that's the idea. This is a pretty direct application of inclusion-exclusion to prove the same formula. So it's kind of fun that you can get the same formula either by doing inclusion-exclusion principle or by playing with these recursive formulas for the number of derangements. So there you go. There's some information about derangements of sequences.